ask you in part A, just first tell me which way the induced voltage is pointing and give me an argument why I don't think you just flipped a coin.
Use the same rule.
Okay. Should the induced voltage, in other words, be driving current clockwise or counterclockwise around that loop?
It should be.
It's decreasing that to the page.
Yeah, I'm getting counterclockwise. Why counterclockwise? Because as the rail falls, the flux into the page is getting stronger, and Lenz's law tells me that any induced voltage I get should be trying to drive current as if it's trying to slow down that rate of change of flux. Since the flux is getting stronger, the induced voltage should act like it's trying to make the flux weaker. It's trying to create new field lines out of the page rather than into the page. Which way does current have to flow around this loop so that the field lines it creates thread the loop out of the page? Counterclockwise. Yes?
Just to be clear, is there a B field below that rail that's moving, or is it just?
Yes, this entire region
Okay.
is suffused in a B field, yeah.
Say clockwise or counterclockwise?
I said counterclockwise because a counterclockwise.
Would make less going.
Yes, any current that voltage drives would be creating. None of these pins work. Any current that voltage drives would be creating new flux lines which point out of the page. They point out of the page as they thread the loop. I know they loop back around this way and they point into the page on this side, but when we say we're trying to slow down the rate of change of the flux, that means the flux through that loop. So yeah, a counterclockwise induced voltage would work here. If you wanted to kind of be thinking in terms of right-hand rule and Maxwell's equations, all that, you could also kind of say a B field, a magnetic flux that's into the page and is getting stronger, that means kind of, it's as if dB dt were that way. I know in this case it's not really dB dt, it's d area dt, but they have the same effect. So you can say it's kind of as if dB dt were pointing into the page. The curl of the E field is supposed to be minus dB dt. So you can say dB dt is pointing into the page, negative dB dt is pointing out of the page. Curl of the E field should be following the right-hand rule around that way. So that's a different way of answering that same question. And I know in this case it's not really the B field that's changing, it's actually the area of the loop, but the effect is the same. And that's one of those things that Einstein was amazed at as he was working his way towards special relativity, is it doesn't matter whether whether the magnet's stationary and the loop is moving, or the loop is stationary and the magnet, you get exactly the same effect either way. All right, so I know which direction the induced voltage is. As that induced voltage, if it does manage to drive current, and since we gave some resistance to that rod, you figure, okay, we will end up driving some current that way. So current's gonna be driven left to right through that rod. Current's going to the right, B field's into the page. Hey, this is what we were looking for. This is why there's gonna be a terminal speed, is we are gonna get an upward force from that current passing through that magnetic field. So again, when we were saying, is the exam cumulative? Well, yeah, it's cumulative in that sense because we are saying here, this relies on us knowing the force on a current which is in a uniform B field is ILB. ILB sine theta or whatever, but in this case all the angles are lining up nicely. So the upward force on that rod does depend on how much current is running through it. Yes?
And just to see if I understand right, the reason we got that, it was originally IL cross B, but because they're orthogonal, you're going to get one for this time?
Yes, because this time, L's that way, B's that way. So that's why I was saying, yeah, I should be putting a sine or a cosine or something in there, but all the angles are lining up so nicely that I know it's going to come out ideal. Yes?
And that L would be just the length of the falling.
Yes, because what I want is the force pushing on this rod. Now there will also be, for example, a force pulling on this vertical rail down here, because there will be current running down that way. The force pushing on that rail will be pushing it which way? Inward. Only that rail's not free to accelerate. I'm assuming it's bolted in place. But you can say, hey, that's interesting. The force pushing it inward, that's like another attempt that nature is making to give negative feedback. That's Lenz's law trying to be sneaky on us. Because if it turns out this rail is slightly flexible, the fact that there's a magnetic force pushing it inward would decrease the area of that loop a little bit. And decreasing the area would lower the flux. So in other words, it's opposing that increase in the flux. So that would be yet another way that nature is sneakily trying to provide negative feedback. It's providing negative feedback by the field lines that it creates in the first place when it runs that current. It's applying further negative feedback by slowing down the fall of this rail. And it's applying yet further negative feedback by trying to squish these rails inward a little bit and see if it can lower the amount of area to swallow those flux lines. Yeah?
So the changing B field, or the change of flux of B field is causing the induced B field
Is-
to go counterclockwise.
Yes. Yeah, counterclockwise.
Just make-
All right, so let's actually run some calculations on this. How strong will this force be? If I was saying I want to know what will be the terminal speed, I'm kind of figuring, okay, presumably if this rail gets going fast enough, this force will counter out what other force? What's the other force on the rail?
Gravity.
Force of gravity. So this force should eventually be equal to mg. Let's see if we can calculate how strong that force is. The actual magnetic flux through that loop at any moment is going to be the B field times the area of the loop. Now, what's the area of this loop? Well, if we call this length here L, because that's the same as I was going to use for the length of that rail, this distance, I could call this whatever I want, x, or since it's a vertical distance, maybe I'll decide to call it y, especially since an x would look like it was blending in with my field lines in the board, so maybe I'll call that distance y. So I say at any moment, the area would be L times y. And of course, the cos phi would just be 1, because again, phi is making a 0-degree angle to the normal to that area. And again, what that phi means is the angle between your B field and the perpendicular normal vector to that area. So there's my flux through the loop at any given moment. Does that create an induced E field? No, not at all. The existence of flux does not create any electrical effects. I could try to fool you on that. I could try to make it sound like just the fact that the flux was there is going to give you an induced voltage. It's not. If the flux is changing, that'll give you an induced voltage. So d flux dt, I could do product rule. I could say, and by the way, product rule works just fine if you're multiplying more than 2 functions. If I was trying to do product rule, I could say dv dt times ly plus by times dl dt plus bl times dy dt plus bly times ddt of cos phi, if that was a thing here. So I could make this some long product rule problem, but I'm more likely to have it changing for just one reason. In here, the B field is constant, L is constant, cos phi is constant, so those are all spectators. The only thing that's actually changing is y, which means d flux dt is the B field times the length of that rod, the velocity that that thing is falling at. All right, so there is my rate of change of the flux. That also means rate of change of the flux, again, is just equal to the induced voltage. So my induced voltage is dLV. Can I use that to calculate that force? Yeah, we're almost there. Yeah, what do I still need to do before I can calculate that force?
Current?
Yeah, I need to find the induced current. Is that voltage going to drive any current?
Yes.
Absolutely.
Yes.
We said induced voltages act just as if I had just physically inserted a little battery with that much voltage. So how much current is being induced here? It's going to be that induced voltage divided by the resistance of that rod. I'm assuming, by the way, that all these other rails are 0 resistance, and this rod is the only one that has any appreciable resistance to it. All right, so there's my induced current. If that's my induced current, how strong is that force? It's going to be ILB, so it's going to be, there's I, then I multiply by L. That L is the same as that L. I could easily make a mistake here. I could easily think, oh yeah, but I already multiplied by L. I took care of that. No, I didn't. L is appearing twice. A wider spacing between those rails is going to give me more induced voltage, but then it'll also give me a stronger force, even once I've calculated the current. So L gets multiplied in twice. I do get L squared. B gets multiplied in twice. A stronger B field, if I triple the B field, that will both triple the induced voltage, which means it'll triple the induced current, and it'll also triple the amount of force that that induced current feels because of this. So again, there is my formula for that upward force on that rail. And it is acting almost like a viscous drag force. If I were to drop this pin off a tall building again, that upward force of air friction that it feels would be proportional, at least at first approximation, to the velocity. So I'm getting something that kind of acts as if it was some kind of viscous drag force, except that it's happening for a completely different reason. There is no physical viscous drag force, there's that magnetic drag. All right, so then if I want to know what that terminal speed is, of course I would just take that force we just calculated and I would set it equal to mg. So to solve for V terminal, I would say mg should be equal to V squared L squared V terminal over R, and I just solved that for V term. So we get RMG over B squared L squared. All right, how could I put some variations on that problem? So again, I'd say, a problem where the B field is static, but the area is changing is something that you could easily expect to find. I might ask you to actually go ahead and take Newton's laws and write me a differential equation for the motion of that thing. Yeah?
Okay. Explain me one more time why is B to the second and R to the second.
Because your induced current already had B in it. And then how are we turning that induced current into a force? We're taking this equation, which is just the force on a current carrying wire in a uniform magnetic field. So I induced already had one factor of B. Now we're multiplying in another factor of B. And for that matter, I induced already had one factor of L, and now we're multiplying in another factor of L. Is that, am I misunderstanding your question, or?
No, I'm not understanding.
So the force is pointing upwards because since the bar is going downward, if what's inside doesn't want to change, so the force is pointing upwards.
Yes, I mean, you could say the force is pointing upwards because it's trying to slow down that moving bar, because the whole reason for the rate of change of magnetic flux is the bar is moving. So you could say, I knew in advance the force had to be pointing upward. However, you can also say, no, even if I'm not thinking about Lenz's law, I'm not thinking about negative feedback, as long as I think about Lenz's law for long enough to say, oh yeah, the new field lines created by that flowing current should be providing negative feedback. Then from then on, I don't need to think about negative feedback again. I can just say, okay, so I've verified, I've reasoned out that the current's got to be counterclockwise. That means the current through this branch is pointing to the right. Current through this branch is pointing to the right. The B field that it's immersed in is pointing into the page. The force is upward. So you should, it's kind of, you should be able to find the direction of all of these negative feedback effects by just kind of straightforward physical arguments that you already know. But then you also want to say, as a sanity check, in the end, everything that happens as a consequence of magnetic induction should look like another sneaky way for nature to provide negative feedback to that change of flux. So I guess one thing I could do if I wanted was say, instead of just waiting until you hit terminal speed and you make those two forces equal, I could also just ask you, what was your acceleration at any moment during that fall? And I would just say, okay, the y component of my acceleration is going to be 1 over the mass of that rod, so I would have to tell you something about its mass, times the sum of the y components of the forces. So I could also say, okay, the acceleration is 1 over m times, I've got an upward force of b squared L squared V over R. And I've got a downward force of mg I could even make that into a differential equation if I wanted, because I could say the acceleration, by definition, is the second derivative of y with respect to time. The velocity is the first derivative of y with respect to time. We'll move that over to this side just for the hell of it. I could say minus b squared L squared over mr times dy dt. And finally, this term has no derivatives with respect to time in it. The 1 over m and the m cancel. So it looks like I would get plus g. 0. So there would be a way I could build myself a differential equation. Maybe propose an ansatz and solve it that way. Probably not on this exam, just because we won't really have time for fiddling around with that. But you said just as far as like being able to integrate what you're learning here into your existing understanding of physics, yeah, we should be able to take the take Newton's laws and start building equations for the behavior of this system. Yeah.
Where did you, I'm sorry, I'm a bit confused for the force of y, some of the forces that make sense to me, but the new acceleration, what is that referring to?
I'm just saying here, the acceleration of this falling rod, I should, just go back to Newton's law and say the acceleration of any object is 1 over its mass times the sum of all the forces.
But didn't we take that into account with mg, or no?
No, this is one of the forces acting on it, but the acceleration will come as a result of all of the forces.
Oh, okay.
So it's not in free fall. G is not the acceleration.
Okay.
G would be the acceleration if we shut down this force, and then the thing would be in free fall.
Okay, so, sorry.
Yeah. Oh yeah. No. That's okay. So yeah, I was using G because my formula for the force of gravity is mg.
So how would you find this acceleration specifically?
I could ask you the acceleration the moment I release the thing, at which point dy dt is 0 and it's falling at g. I could say if it, in order to ask you the acceleration at a given moment in time, you've got to already have a solution to this thing proposed. So you could plug in an ansatz and see if it works and all that kind of thing. But instead of asking you what's its acceleration at a given moment in time, maybe I would ask you what's its acceleration when it's moving 5 meters per second. Because then you don't yet need to know how anything depends on time. You can just say, okay, that's when I'll plug in 5 meters per second for that dy dt. Yes?
So in general, when we want to set up, when we want to find differential equations, we want to take derivatives, want to start taking derivatives on both sides.
Yeah. Usually my way of setting up a differential equations, I kind of try to think, what's the highest derivative that I'm going to see of my function in here? And I usually kind of try to solve for that one. So in this case, I said, as I'm looking at this, acceleration is the second derivative of y with respect to time. I know as I've been thinking about these forces that one of them is going to depend on the velocity, and that's the first derivative. I know there's another force that won't depend on position or velocity, and that'll be the 0th derivative. So I kind of said, okay, it'll be best if I kind of get acceleration by itself on one side of the equation, and then go from there. Now again, I'm probably not going to emphasize the crafting of differential equations on the exam because again, it's not high enough on my list of priorities to be worth spending precious time out of that 2 hours and 50 minutes. Hey, what if instead of a uniform B field, what if I wanted to give you a varying B field? Which would be a bigger challenge? Suppose I told you this B field is actually, instead of just being there, it's being created by something. Maybe this whole thing's taking place inside a solenoid, in which case you just calculate how strong the B field of that solenoid is, and then it's just there. Maybe this whole thing is taking place near a current carrying wire. Maybe the way I got this B field is I was actually running current through this wire over here using an outside voltage source. Which way should I run the current if I want the B field to look vaguely like that? Upwards, exactly. So maybe I'm running a current upwards like that.
Noise.
And I tell you this distance could just be called x naught or something like that. And I tell you L. Could you now answer the rest of the problem for this situation? What would I need to change?
Yes.
You would need to integrate the B field.
Yeah, instead of writing that phi sub b is the B field times the area, now I would have to say phi sub b is the integral of the B field with respect to area. So I might do a bookkeeping scheme where I divide this area into a bunch of little vertical strips like this. So I could say, all right, maybe my bookkeeping scheme is X could be my distance away from that wire. Dx could be the width of the little strip that I'm looking at right now. The strip is not a physical object, but it's just saying if I want to find the total flux, I'll find the flux through this little stripe, and then this little stripe, and then this little stripe. When I've added them all up, I'll be done. So I could say, in that case, something like d flux, the amount of flux I'm getting through that one little stripe. Would be the B field in that stripe times dA times cos phi. Well, what will dA be? It'll be the full length of that stripe, which is still y. So that's, my y, my vertical height that the rod has followed still comes into this. So I could say, okay, this is, my B field will be mu naught I over 2 pi. 2 pi times what with my bookkeeping scheme?
R.
What's R?
Distance from the wire.
X, exactly, my distance from the wire. So mu naught I over 2 pi x times dA, which is going to be y dx, the full height of this stripe, which is y, times that little width dx, times cos phi, but cos phi is still 1. So there's that little contribution to the flux. What is the total flux at this moment? I get it by adding up all those little contributions. So I can pull everything that's not dependent on my bookkeeping variable out of the integral. That means I pull out, of course, the mu naught over 2 pi. It also means y. I mean, y is something that's changing as the problem goes on, but it's not changing as I look from one of those little green stripes to the next one. It's not dependent on my bookkeeping variable x. So I can actually pull the y out of the integral. And it looks like I'm just integrating 1 over x dx. What are my limits on x?
Negative L over 2.
0 to L.
Except x means my distance from the wire is the way I've been setting it.
0 to x naught plus L over 2.
Yeah, so I'd say x naught to x naught plus L is what it looks like to me.
What happened to the I?
What's that?
What happened to the current I?
The current's still flowing, but the current, see, my job now is I need to first calculate this flux, then I need to take ddt of this flux, and that'll give me the induced voltage. Then I will use that induced voltage to get I. So I is still there, but and this is an important lesson in problem solving in physics. This is one reason why a physics degree is considered just kind of a good preparation for any career where you do a lot of thinking, is it trains you to kind of say, let me keep careful track of which step of the problem I'm working on right now. So yeah, you say in this case, yeah, the I is still flowing and it's totally gonna be important and all this stuff over here is gonna happen later, but what I'm doing right now is I'm trying to do this step. I'm just trying to find the magnetic flux at some particular instant when this thing's at position y. So yeah, as it turns out, so this integral is just going to give me natural log of x, which when I evaluate the limits, this is now saying the flux of B field through that loop is going to be mu naught over 2 pi times y times the natural log of x naught plus L over x naught. So that takes the place of what I got over here, just B times L times Y. How would the problem go from there? Well, my next step is going to be to say, what's d flux dt? And you notice, well, I've got this natural log, and I might say, oh shit, so the derivative of natural log is 1 over the argument. No, I'm not taking d dt. X naught doesn't depend on time. L doesn't depend on time. This is all just a big ugly looking constant as far as the next step of the thing goes. If I'm taking d dt, what's the only thing in that expression that depends on time? Y. And once again, that introduces my velocity, and I'm off and running that way. So that, that would be not a particularly difficult integral to solve. It would be something that's kind of reminding you, let me not lose my place in this problem. Let me not forget the purpose of the step I'm doing right now. And actually, in the long run, that is a skill that will stick with you long after you're kind of vague on a lot of the actual specific knowledge that you gained studying physics. this is why we always tell people, yeah, no, physics degree is great preparation for life, whether you do this or not, is, man, it teaches you to be good at problem solving. And part of that is it teaches you to make sure you don't get ahead of yourself and you're keeping track of what step of the problem you're on right now. Yeah.
So when we just care about and look at the little contribution to the flux, we have mu naught I over 2 pi x.
Yes, because I was saying the little contribution to the flux through that green strip that I drew is going to be the B field, so that all tells me the B field, times the area of that green strip, which was y times dx. By the way, the reason I used a green strip, I could have instead broken it into little pixels, and then it would just be dy times dx. But I would realize, oh yeah, there's nothing in there that depends on y, so when I integrate out the dy, it'll immediately just give me the full y at this moment. So instead, I was kind of saying, instead of pixels, let me just kind of skip a step and go straight to breaking these into these vertical strips like that. So the reason I was getting away with that is my B field was uniform all the way along that vertical strip.
So yeah, we have the little contribution, and we have I in there as part of that little contribution. But then when we look at the total flux of B field, the I is not necessary. It's just mu naught.
Oh shit, I'm sorry, yeah. No, this was,
Yeah.
Okay, there are two I's in this problem. There is the current in this wire that's creating the B field, and then there's the induced current. When somebody, I forget who now, was asking me earlier, what the hell happened to I now realize what you meant. You meant this I.
Yes.
And yes, what happened to it? I left it out through a typo. But yes, there are two different currents. There's a current that's creating the B field, and there's the induced current, which is responding to the B field.
So yeah, you're using the current through that first wire to find the current that's induced in this other
In
wire,
that loop,
in that
yes, absolutely. The only, now you could say, will there ever be problems where those are actually both the same current? The current that's creating the B field is the same as the current that's induced? Yeah, that's what a solenoid is. So that's what an inductor is the current through that solenoid is both the thing that created the B field, and it's also the, it can be the response to that induced voltage from the B field. All right, so does that problem look pretty good?
Yeah.
All right, let's try another one. If we've done one where there was an induced voltage because the area was changing, let's try one where there's an induced voltage because the B field is changing. So this time I'm gonna say I could make a solenoid, and we could say the B field is just blah, 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 mu naught times the number of turns per unit length of the solenoid times the current through it. I could make, this might be fun. I could do, let's do this. I'm gonna do a loop of wire instead of a solenoid. Why a loop of wire? Because I'm assuming that the formula for the B field in a solenoid is so simple that if I give you a solenoid, that's just kind of something that nobody will have any trouble with. So let me put something where there's at least a little bit of interest to it. So I'm gonna have a loop of wire like those little Helmholtz coils that I always used to bring out, where there was that loop wire that goes like that. So we'll say this thing has radius A. The number of turns in this Helmholtz coil is N. And near the center of it, I'm going to place a very tiny little triangular loop of wire that's disconnected from the outside. I am going to be running current I around this Helmholtz coil, and I is going to be increasing at a steady rate. At time 0, the current that I'm running is going to be 3 amps. At time 2 milliseconds, the current that I'm running is going to be 9 amps. And I'm going to say the current increased at a steady rate in between those two moments. All right, so I'm running that current I around this outside loop.
So B field.
Can you tell me what the voltage is induced in that little triangular loop? And the triangular loop, I'll say, just has one loop of current of wire in it. If at the end I say, oh man, that's a pathetically small voltage, One thing I could do about that if I wanted would be to say, okay, instead of one loop of wire, let me put a billion loops of wire or something like that, then I'd get a billion times more voltage and I'd be happy. I will say that the length of the base of this triangle is B, and that it's an equilateral triangle.
I think so.
Okay, yeah, the induced, so the current is running counterclockwise here, which means the B field at the center of the loop where my triangle lives is pointing which way?
Ouch.
Yeah, the B field created by this current at the center is pointing out of the page. So I've got a B field pointing out of the page all through here. If this loop is tiny enough, then I can approximate that B field as being what?
Uniform.
Yeah, uniform over the area of that triangle. And do I have a formula for how strong it'll be?
Yeah.
We do
Yeah.
actually. It was kind of the first step. We had a formula for the B field anywhere actually along the axis of a current carrying loop like this. The formula that we've got, and it's on your equation sheet, is mu naught over 2, yeah, it'll end up being like mu naught over 2 pi times the area of that loop, which is gonna be pi a squared, and then it was divided by z squared, your distance along the axis, plus a squared to the 3/2 power.
I think there's an I in there.
Oh, yes, and
And-
of course it depends on how much current is running through that outer loop and on the number of turns in the outer loop. I think that takes care of most things that I might have forgotten up there.
Right.
Does that look like the right formula for the field on the axis of a loop?
Doesn't it end, like the one on the equation sheet doesn't end.
Because I was just doing a loop of one turn, but
Yeah.
you can say, okay, I can, if I've got 5
Yeah.
turns, I just get 5 times as much B field and so on. Okay,
Yeah.
so from that, in this case, I can use that formula. How do I customize it? How do I simplify it?
We say that we're not a Z distance away.
Yeah, Z was the distance from the center of the loop along that axis. In this case, Z is 0. So interesting limits on this one are if Z is 0, my B field is just, I can cancel those pi's if I want. So my B field is just mu naught over pi, and this will be a squared, and this will now be a cubed once I zero out that Z. So this will be just pi a times I times n. So there's my Z equals 0 limit. There is another interesting limit to this equation. What do I get as Z goes to infinity?
Oh,
0.
I mean, I know I get 0, but it goes to 0 how?
Wait, the limit of what again?
If I take the limit as Z goes to infinity, I take the limit where I'm very far from that Helmholtz coil.
What's the point charge?
That's not like a point charge.
It's,
It becomes very small.
Was that? My Helmholtz coil itself starts acting like a very small loop of current. What's the name for a very small loop of current? Magnetic dipole. This should give me the magnetic dipole result if I let Z go to infinity compared to A. So if Z is much greater than A, then I can kind of say, at least at first, I'll ignore the A. Maybe I'll need to put it back in later if everything cancels and maybe do a power series expansion. But at least at first, I can say, if Z is much greater than A, let me ignore the A. This gives me Z cubed. So what do I get in the limit where Z is vast compared to A? I get that my B field is mu naught over 2 pi times, and I'm going to leave the pi a squared there times the current, because I'm going to say together, that gives me my magnetic dipole moment, the thing that the physics community stubbornly continues to call mu, even though I've explained to them that we need to call it something. Oh man, does anybody have a good Elvish rune, speaking of those, available for that thing? It's a perfect place to start introducing Klingon or Elvish or something like that into physics notation here.
Why not use this help for Bluetooth? Like a
Because I don't remember what it looks like.
like a B almost.
Triangular B.
We're just trying for
Like a line.
Thingy. Okay, so I've got
It's not very concise.
magnetic dipole moment is represented by a cat until I think of something else. So magnetic dipole moment over z cubed. And that cat represents the magnetic dipole moment, which for a circle is I times pi a squared times the number of turns. One thing that I asked you about on the last exam was, what if it's not a circle? What if, for example, it's a trapezoid? So what I was asking you, hey, there, you had that trapezoid, and you were trying, the main part of the problem was finding the field created by the trapezoid up at this point. And by the way, I was glad that everybody figured out pretty much universally that the field created by those two legs of the trapezoid is 0 because they're headed straight toward the point where we were measuring it. Then at the end, I casually asked you, what if I want to measure the field at a different point? One that's way off axis this way. Not many people got that, but if you did say, wait a minute, I can make a leap of logic here. That trapezoid is just going to look like a little magnetic dipole moment if I'm clear the hell off here. Then the field should be going as 1 over z cubed. And in fact, I think I gave extra credit saying, can you actually give me an expression for the field? Yeah, it'll be the current times the area of the trapezoid this time instead of the area of a circle. It'll be the current times the area, and I think there was only one turn of wire, so the current times the area times 1.
I don't understand why it looks like a dipole when you don't think so.
Because the way you make a magnetic dipole is you take a little loop of current and you're on the axis and you just move very far away from it. If I say, okay, let's draw an axis from there, clear the hell out here, that's what that is. That's a little loop of current. Doesn't have to be a circular loop of current. In the same way that we say anything that's kind of a lopsided distribution of charge counts as an electric dipole, anything that's a little loop of current, I mean, if you're far enough away, you're not going to be able to see the details, whether it's a circular loop or what anyway. So yes, that little loop of current is going to end up acting like a magnetic dipole. I think what I finally chose as the place where like full credit for that problem stops and extra credit begins is I was saying, okay, realizing that this is a magnetic dipole and therefore that the field goes as 1 over distance cubed takes a leap of logic, but that's kind of one that I was saying, okay, that's something that I'm going to, make it part of getting full credit on that problem. Then anybody who actually was able to write the expression, right, the area of that trapezoid times the current around it, and say that is going to fill in for this kitty cat here. That is going to be the magnetic dipole moment. I counted that as extra credit because we hadn't actually talked about irregularly shaped loops. But I figured, the leap of logic from saying, okay, the loop does not actually have to be a circle in order to have a 1 over distance cube field. That seemed like a reasonable thing to, yeah.
No, I'm just stretching.
Oh, okay. So yes, in this case, I could have, if I wanted, put this triangle clear the hell out on that axis. And then we would be using this version of the B field strength. I could put it at the center of the loop, which we did, and then we'll be using this version of the B field strength. Or I guess if I wanted to, I could put it at any point in the axis, and we'd be using this one. But one way or another, oh yeah.
Sorry to interrupt, I was just curious to make sure that I understood the reason that looks like a magnetic dipole is just because you're looking at the top and bottom wire?
No, because I'm looking at the full loop of current, not just the top and bottom wire. A magnetic dipole is, the simplest way of realizing a magnetic dipole is this, a little loop of current. You are or at least the formula we got for the field from a magnetic dipole, the one that we say is u naught over 2 pi times kitty cat over z over distance cubed.
Yeah.
That is assuming that you are on the axis of that loop. So here I'm saying that trapezoid is a loop. It's not a circular loop, but the shape of the loop doesn't matter. But no, all 4 sides of that trapezoid are kind of part of the field. If we said these 2 sides created 0 field, these 2 sides create 0 field at this particular point. Okay. They don't create 0 field everywhere in space. Yeah.
So when z is equal to 0 in our expression for the B field, I'm not quite understanding that algebra.
In this expression?
In the bottom one that's boxed. Shouldn't the pies have canceled and the two?
Yes, the pi should have canceled, I'm sorry.
Okay, and the two is there.
And the 2 is still there. Oh,
Okay.
in fact, I think the 2 is what I meant to write instead of the pi, yes.
When you have your current fluxes.
And I think that's also on the equation sheet, just as the special case of the field near the center of a circular loop. Yes.
That top one in blue, is something from,
We worked that out as a superposition integral in class, but that's the B field on the axis of a loop. In fact, we did a lab where you investigated that one also. Remember, you had the lab where you had the B field sensor and you were moving it back and forth along the axis of the loop, and we were actually graphing the field and seeing if it came out to that again, to a value that looked like that one.
and then you found that it was over Z cubed just because it looks like a dipole.
Well, from this,
From far.
no, from this one, I found it was over Z cubed because I just plugged in. If Z is much greater than A, then that A squared is a negligible contribution. The Z cubed came from Z squared to the 3/2 power. So on this one, I'm saying, no, that's how I know that dipoles go as 1 over distance cubed. Then on the exam, when I said, can you tell me that this one goes as distance cubed? That was supposed to be a little leap of logic where you said, even though it's not a circular loop, I'm pretty sure that a loop of wire is a loop of wire. If I'm far enough away, the details of the shape are not gonna matter, but the fact that I've got that little loop of current is gonna matter. Much in the same way that you start out with an electric dipole, saying if you take a negative charge and a positive charge, I'm gonna separate them by distance A. But then if later on you've got a water molecule, and the water molecule kind of has a charge distribution that looks like this, and the place near the oxygen is positive, and, negative. The place near the hydrogens is positive. Okay, it doesn't look like 2 point charges, but that lopsided charge distribution from a great distance will give you the same 1 over distance cubed behavior as this similar lopsided charge distribution. In the same way, any shape of loop of current, if I'm far enough away and I'm on the axis and all that, is gonna give me behavior that should resemble the simplest loop of current I could make, a circular loop. Okay, so coming back to this guy, I'm ramping the current up from 3 amps to 9 amps. We have chosen to place our little triangular loop at the center of that circular loop. Although again, we could have placed it anywhere along the axis, or we could have placed it at a very great distance and used that dipole approximation. Either way, we've now got an expression for the B field that that triangular loop feels. Help me finish the problem. How will I find the induced voltage around that triangular loop?
You have to change the B field.
Yes.
In some way.
I need to change the flux, which in this case we'll do by changing the B field, although we said in this case we changed the flux by changing the area, that worked too. How would I write an expression for the flux?
Based off the change in current.
Yeah. Magnetic flux, again, I mean, magnetic flux is the integral of B dot dA, but in this case, can I say the B field is uniform?
Well, at that point.
B field needs to be uniform over what region? If I'm trying to do an induction problem, if I'm trying to say, can I get away with saying magnetic flux is just B field times area times cos theta, or do I need to do an integral? What do you think? In this problem, do I need to do an integral, or can I get away with saying the B field is uniform? Yeah, so the B field needs to be uniform over what region?
Triangle.
Over that, loop that I'm taking the flux through. The B field's not uniform over all of space. It's greater if I'm near the wire up here. I get strong B field coming out of the page and strong B field going into the page on that side, and they're, other way around. Out of the page there and into the page up there. They're getting stronger and stronger as I approach the wire. And none of that matters to me because the loop that I'm taking the flux through is this little triangular loop in here. And we said that B is much less than the radius and all that kind of thing. This guy is seeing a roughly uniform B field. Kind of like we're seeing a roughly uniform gravitational field in this room, because this room is such a small region that the ceiling and the floor are both about the same distance from the center of the earth and all that kind of thing. Exactly the same reason here. This little triangle does see a uniform B field. So I can say the flux of magnetic field through that triangle is just the B field measured at the center of the loop times the area of that triangle. I'm putting the subscript there just so I don't forget what area and accidentally take the area into a circle or something like that. Times cosine of phi, only again, phi is 0 degrees. And again, that phi is the angle between the B field and the normal vector to that area, and they are both pointing in the same direction. Okay, so for the B field, I've got mu naught over 2a times I times the number of turns in my big coil. For the area of the little triangle, what have I got? What is the area of a triangle?
1/2
Base into height.
Yeah, 1/2 the base times the height. That's not really the main point of this problem, but if I've already said the base is b, anybody want to tell me really quickly what's the height of that triangle? B times
Half the base. Yeah.
36, or, you know, the
Yeah,
little triangle is 36
3 over
degrees.
2b.
Yeah, b times root 3 over 2. B times the sine of 60 degrees, in other words, because this side is b, that side is b times the sine of 60 degrees. So the area of that triangle is 1/2 times the base times the height, which is root 3 over 2 times the base. Or my total area is root 3 over 4 times b squared. Okay, so there's my area. Root 3 over 4 times b squared. Cos of 0 degrees is 1. I remembered to include the number of turns in the wire. I think that's pretty much it for finding the flux, which means that's my induced voltage, right?
No.
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 Why is that not my induced
No
voltage?
change in
That's
flux?
not saying there's a change in flux.
Yes, the existence of flux does not induce a voltage. The rate of change of flux induces a voltage. So at that point, all I've said is the magnetic flux exists. That does not impress Michael Faraday. I need to say the magnetic flux is changing, then Faraday's law gives me an induced voltage. So what is it about that whole expression that's going to cause the flux to change?
There's a change in current.
Yeah, there's a change in current. I mean, I could really kind of say any of these things. I could change the area of the loop. If the loop was actually shrinking or expanding, that would cause a change in flux. If the number of turns of the loop were changing, that's kind of hard to do real time unless I'm, I don't know, using transistors to cut current in and out of different turns or something like that. If the area of this little piece were changing, then it would be back to a problem more like this, where the changing flux is due to changing area. So any of those parameters there could be things that were changing and were giving me an induced voltage, but in this case, it's the current that's changing. So I could say, one way for me to do this is just to say, change of the B field, ddt of that flux. I could look at this and I could say almost everything in there are just constants that I can pull out front. Root 3 over 4 and the 1/2, I'll make that root 3 over 8. I've got my mu naught, that's not changing. I've got my area, or my radius, I'm sorry, that's not changing. I've got my number of turns, that's not changing. I've got b squared, the size of the triangle, that's not changing. But the current is. Now, how would I find di dt? Do I need to take a derivative? No, I mean, I could totally give you a problem where you have to take a derivative. I could have said I is such and such a function of time. What's a very popular function of time for me to give if I was going to give the current as a function of time?
Charge capacitor.
Okay, yes, I could be charging a capacitor and use that current. I could do that. And then I'd be, Q naught times 1 minus e to the blah, blah, blah. Or I could be discharging a capacitor. I've just got the e to the minus blah, blah, blah. What is possibly, though, the most popular function to put in for current as a function of time? AC current. I equals I naught cos of omega t. Because that happens all the time. So I could have here said, oh yeah, I equals 50 amps times cos of omega t, where omega is such and such. Or hell, maybe there's an LC circuit involved and I have you find omega by 1 over root LC or something like that. That could be fun. But yeah, I could give you, I could make it so that you have to actually take the derivative of some function. Or we could do what we did here and just say, looks to me like the current changed by 6 amps. And it took 2 milliseconds to do that, and I said it was changing at a steady rate during that 2 milliseconds. So I could also just say di dt is 6 amps over 0.002 seconds, or that's 6 times 500, which ends up giving me 3,000 amps per second. So it looks like my DI/dt is 3,000 amps per second in this case, and we're holding it steady during those 2 milliseconds. So during that 2 millisecond interval, now I've got my induced voltage around that little triangular wire. If we had given you the resistance of the triangular wire, or if we gave you some information you could use to calculate the resistance, we could now go on and use that induced voltage to find an induced current. I could use that induced current to then find an induced magnetic field created by that little triangle and so on. So, you know, you can keep this chain of cause and effect going for as long as you want, but yeah, once, as we always say, now that I have found that induced voltage, what effects will it have? Exactly the same effects as if I just hooked up a little battery of that voltage. So, you know, that could be the start of a whole nother part of the problem if we wanted it to. Yes?
So we went over like changing area, what it does, we're changing B field. So,
Yeah.
The angle between the natural vector and the something else.
The angle between the normal vector and the B field,
Okay.
yes.
That could be changed.
That could be changing. And if I was saying here, you know, what's the most common function you'll see that would let the current be changing with respect to time? And although in this case I didn't use the most common function, I just said, well, no, the current's just changing at a steady rate. We said, but you know, a lot of times you'll see the current, an AC current, where I is I naught cosine omega t. A lot of times, if I wanted to give you a problem where the angle between the B field and the normal vector in my loop was changing, there is a very popular class of problems where that does happen. And I'm talking about problems, I mean, what's the name of a device where the angle between those two things is changing?
The turbine.
The turbine or the generator, exactly. This is how electric generators very often work, is the angle between those two things is changing. We had the little water-powered ones that we were passing around in lab that time where you had, you know, you could see through the translucent plastic a loop of copper wire, and you had that little magnet that was spinning as you spun the rotor on the generator. So you were changing the angle between the magnetic field and the normal vector to that loop. So yes, we could totally give you a turbine problem. So does this one sound like we've kind of exhausted everything we can do on that one and all the little random variants I could name that we could have done differently?
Yep.
All right, let's do a turbine. Okay, so if we're gonna make this a turbine problem, again, I mean, it's not like there's no such thing as product rule. It's not like we can't give you a problem where more than one of these contributions to the flux is changing. But if we're kind of trying to stick to only changing one thing at a time, then if I'm changing the area between the B field and the normal vector, then I guess I'm not going to be wanting the B field to change. And if I'm changing the angle between the B field and the normal vector, I'm not going to be wanting the B field to change, and I'm not going to be wanting the area to change. So, give me a way to create a uniform B field. Solenoid, yeah, we haven't done a solenoid yet, let's do a solenoid. So I'm going to set up a solenoid.